Good morning, everybody. My morning has been very good, very intriguing, because I'd been nestled in my home office, talking to people virtually, and finally I get to see so many bright minds here. So, extremely a good day. Pandemic was a dark cloud. I don't know if it still was. It is a dark cloud. But, my 7-year-old daughter looks at life with optimism, and I've learned to look at it a little bit that way. And every dark cloud has a silver lining. And the silver lining for the pandemic essentially is digitalization, and primarily virtually connecting us seamlessly, which we never thought would be able to in the past, right? And one such concept that was born during this pandemic is the concept of digital triplet. And today we'll talk a little bit about it, and I'll look for questions after that. Oh, I'm having issue with moving my slides. Okay. While they try to put up the slide, let me start by expanding my introduction to demonstrate why I'm qualified to speak about this. In addition to what Scott told me, it spoke about me being the Chief Technology and Strategy Officer with Waygate Technologies. We pride ourselves in Waygate for being the market leaders in the industrial inspection space. We come from a legacy which is more than a century old. We have the people who actually commercialized the first ultrasound for industrial use, the Kraut-Kramer brothers, is a brand that is a part of what we do. Same with Seifert, who worked with Röntgen on X-ray and trying to industrialize that part. And with that, I think one of the big aspects of this is inspection and the data that we get from inspection. So now you may ask, what is industrial inspection? What is NDT? What's non-destructive testing? Think about it in a way, when you broke an arm or broke a leg, you went for an X-ray, or you've gone and looked at ultrasound for some reasons, or you have had a visual inspection by your doctor to say something is wrong or right. And industrial inspection is pretty much similar to this, basically not breaking something and looking in, but really being able to look at things deeper than the surface through technologies, similar to X-ray and UT. But the thing is, we don't do it for patients, you do it more for things and assets. And and in the spectrum of the electromagnetic spectrum, we can have multiple different penetrations and sizes that we can look at and essentially be able to look much deeper into the asset than we could normally do. Essentially, we're trying to make the invisible visible for all assets. Being the healthcare of the industrial space really means that our patients don't breathe. So what that means is we scan a cell phone, we scan a circuit board, but also we scan aircraft engines, we scan automotive parts. And yet as a consumer, you probably have never really heard about industrial inspection. With the car that you drove in today or the flight you took today, you really probably never thought about it. And the good part is the most successful inspections are the ones that you don't really know or think about, because if a battery blew up, you would know. So things work because they're being inspected and safely looked at. With all of this as well, unfortunately, manufacturers or people do not want inspections. They want an asset with no defects. That's their aim. It's not to do inspection, it's not to do certain things, look for defects, but really a part without defects. So again, drawing the analogy to healthcare, a doctor's visit is one that you don't like when you don't want to do. That's the best doctor's visit. But if I told you that by going to a doctor, you could increase your longevity, I would say you can increase the chances of knowing what might go wrong, and then you can fix it, then you might be interested. Then you might want to go for it. And which is exactly, I think, with that in mind, we also thought, wouldn't the asset owners have a higher return of investment if they primarily looked at this data not as a sunk cost, but more as a value-added data that can provide additional insights? And this, just hold that thought a little bit. When you look at an example, and a closer example of an automotive, there are multiple types of inspections done. And focusing on the engine, if you look at it, there's like 3 tiers, 3 different suppliers that do different inspections. There are 22 types of inspections done with 5 or more modalities that they use to do it. But what happens is this data is fragmented, isolated, and really people look at it whether there's a defect or not and throw away the data. Just by interviewing a bunch of our customers, we found out that there was 28 terabytes of data that were just checked and thrown away. Now, this is all sunk cost for the manufacturer. Now, if you put an abundance mindset to this whole thought and saying there is an array of information, there is a lot of data out there, there is a lot going on with this data that can give you insights that other sensors or other methods cannot give you, then you think about how you convert that into a valuable data and a valuable insight that can return value to you. And so with that in mind, we think about it in 3 simple steps. 1, first of all, from that car, how do you acquire all that data and contextualize them in an harmonized interface? And once you do that, you already can start building a passport or a digital passport for that part, saying when it was born, it looked like this, when it was manufactured, it looks like this, and when it's in service, it looks like this. And really link back the whole life of what was happening. The next step is really analyzing. And now that you have all the data, you've contextualized it, you've put it together, then you think about what can I learn from this? So are there certain design practices or manufacturing practices that are causing certain defects or certain problems? How do I improve my design to really think of how I could improve the final product? And using AI and machine learning, you can also look at similar parts in the past and draw all the data together to drive this. And the last part is really the act part, where yes, we can give insights for a human, but then how do you take a human out of the loop and improve design and the processes on its own through a virtual feedback loop? And that is, if we could do that, every part that comes out is going to be better than the part before. And eventually, you're going from detecting defects to totally avoiding them. In today's world, the concept of digital twin is very well understood. It's the ability to combine digital simulation of a part through its design and life cycle to enable the prediction of its process and performance under various conditions. Now, an entire aeroplane can be simulated entirely on a computer, and we can actually show when a bird strikes what type of damages can happen and does it have the ability to land safely. Now, add the inspection layer that we talked about. This gives you a real-world view on the current condition of the part. It also talks about the actual defects, the material properties, thus connecting the real-world view with the digital simulation from the digital twin. So going back to the same example of an aeroplane hit by a bird, now we can look at multiple engines that were hit by a bird, and we know what type of damages were done, and you collect that data together and really build up an enhanced simulation that would give you much more accurate prediction for us to really say what the condition of the engine is, and therefore, is it safe or not safe to go ahead. So it's really enhancing the whole concept of simulation and adding that layer to it. Now, there is a layer that is added, but also I think there is a little bit to it around a paradigm shift where you start to connect the real world view and the simulation to enhance it. And this paradigm is what we call digital triplet. So the additional layer of the real world that connects to this. And imagine in the existing process, if we start adding this regularly, there are multiple value-added optimizations that can be driven. Be it manufacturing, be it design, be it process, be it yield. You can increase yield efficiency because you learn and know the defect types, you know what kind of material properties would react to what, and then you can link all that together. Now let me take you through an example of castings. Casting simulation tools are routinely used to check the pour temperature, to look at the ability of pour rates, and so on and so forth. And the cast part is then used for future simulations and really to understand whether it works, whether, when will the temperature go high, how do we improve the casting processes, how do we improve the parameters, and so on and so forth. However, now when you add the level of inspection, it starts to give you more information around the defect profile of the castings. It also provides you the material properties as seen. And in this case, we use an X-ray CT technology as an inspection to get that data. And then you embed that data into the actual simulation for multiple lines of castings or even individual castings. And further, what we can do is this defect information can be included in the reduced order model for the casting process to create a more optimal set of casting parameters that not just increase the process efficiency, but in addition also minimizes defect occurrence in the future parts. This is truly game-changing. And with this yield optimization, there is productivity, there is quality, and there is safety. Another example is the additive. It's manufacturing in a box. A very good example to show how we can apply acquiring, analyzing, and acting on that data to improve the simulations and the design. Specifically because it's done in a box, every improvement made through the process is fed back, and every part that comes off it is a better part than the part before, which sincerely means that we are in a journey to reduce defects to the point that you start getting parts that are completely defect-free, which is what we said initially. Our manufacturers and asset owners are not looking to do inspections. They're looking to not have defect-free parts. So this is the intent to drive this. And in conclusion, where this is an ecosystem, is it another digital tool? Do we have to add it to something else? So on and so forth. And we're trying to understand where it places in the customer ecosystem. The industrial inspection ecosystem fits perfectly into any existing customer ecosystem to provide this multi-generational value with the digital triplet, leveraging the acquiring, analyzing, and acting steps, and linking into the existing simulation tools or the digital twins and the ERPs and so on to create that improvement and drive value through this digital triplet. I hope I left you with this new concept, and I'd like to have some questions and thoughts from you as well. Thank you.
Thank you, Aru. Sorry about the technical issues there. Thank you so much. Yeah. Okay, I have had some questions come in, as you anticipated. Are there any questions from the floor, by the way, before I go to some of the questions I've got here? There's one right at the back there. Just 1 second, please. If you can take the microphone, and if you just say your name and where you're from, please, first.
I'm Harun Yusuf, and I work at research in ampometry. My question to you is, how do you model this kind of data? Do you model it like in a graph format? Do you model it in database? How do you model it, and how from your modeling, how do you then extract all the insights that you're claiming to do?
So how do you model the data? How do you get the insights from that?
The data, we don't actually have to model the data itself, because when you do an X-ray, you see a part of the asset that looks exactly like it, but gives you more information. What we do is contextualize that information. We start to take that information and say, this bottle, I've scanned it, I know more about it because it's opaque, and we start to contextualize the defects in it and say, these type of bottles have these type of defects, and then we connect the data. These are not simple time series data, they are high 3D volume data. So essentially, the challenge here is contextualizing, but also contextualizing and managing the data itself and storing the data, because today, not a lot of people look at 3D volume data. It's a lot of information. When you look at the metadata that is associated with it, it's a lot of information. The idea is to really contextualize it. So the data is available. It's just people haven't been using it.
I can do it.
Okay, I've got some questions here as well. Now, digital triplet is not a phrase that I've heard a lot before, and you mentioned. Well, did you coin this phrase?
A colleague of mine did.
Okay, excellent. Okay, I didn't know it was a phrase of yours. You mentioned the example of the aircraft. Can you give us some other examples of where this might be applied?
So we have, for example, when we look at services of engines, aircraft engines. So we start to look at when the engine is born. So material properties and so on. We do CT scans to look at the material properties. Sometimes if it's steel and so on, we use ultrasound scans. So we start with that, and then we move to the design phase where the engine is being designed. So every time there's a different design, we do the inspections, store that data. As I said, there's a lot of metadata that needs to be contextualized, but we link it to the asset structure. So we use the structure to link it. And then once we find the right design, we continue, it's born, it's now learned something, and now we continue to manufacture it. We look at that as well. And then in the end, when it's in services, every time we do a visual scan or an ultrasound scan, we get data back. We start to link that. But what also we do is we don't only look at it as one engine. We also look at it as a fleet. So engine type, and saying these are certain engine types that give certain outputs. So how do you look at other engine types? And then you use AI and machine learning, and the more data you feed in, it learns faster and gives you a holistic view of this.
I can sort of understand that from a deterioration or a wear and tear point of view with an engine, but you mentioned an example of bird strikes, for instance, and obviously all bird strikes are not the same, and they have different impact. So how, you're saying you effectively run the data from multiple previous bird strikes.
Correct.
To get the most, what's the word I'm looking for, to get a typical solution based on
Absolutely.
What's happened.
And with the digital twin, because digital simulation tools, we're not trying to recreate the digital twins. What we're trying to do is add the layer on top of it, right? So digital twin is already simulating these various conditions. That's what digital twin does.
Yeah.
By adding this extra information, what it does is it starts to learn faster, historical data, defect profile, and more data about things that you usually would not know in a simulation. So it's connecting the real world data of what's happened and then the simulation data together.
Okay, well that makes perfect sense. No one else has been doing this?
Surprisingly, I don't know.
Okay, right, there you go.
But people are doing it now. The last couple of years I've seen a lot of people doing it. They don't probably call it digital triplet, but pandemic has definitely pushed people to think a little bit more around this.
Okay, yeah, another question here. Just wait for the microphone, please. And again, just state your name and where you're from, please.
Yeah, my name is Arun Kumar. I'm coming from Stepstone. I'm a principal BA developer. My question right now is what you touched right now about you get the output of your data, and then for the stimulation, how do you train, and then how do you make the, okay, whatever the output is right, and then you can able to go and adjust your model and go and train kind of thing. Do you need to have some sort of benchmark whether, okay, this is the right one based on which pattern that the model is working right or wrong, whether how do you train, how do you retrain your model?
It's a very good question, because you can, when you think about machine learning, you can go from completely giving it all the conditions to leaving it completely open to teachable ADR. It really depends on what part, what stage an asset is at, and what criticality an asset is at. If the asset is at a very early stage and the criticality is low at that point, we use what is called a teachable ADR, teachable AI, so where it can learn from all the data that's coming through. However, for example, for an aircraft engine, it's a critical part, you cannot mess it up. So obviously we use the experts to start already giving us input. So there is a human in the loop to create conditions, give conditional based AI, and then improve from it as we get more data. So it varies depending on the criticality and the stage. But we use all types, starting with conditional, completely conditional AI, saying, if it's A, do B kind of thing, to completely learning from, I don't know what it is.
Okay, thank you. Right, I want to come back to women in STEM that I mentioned at the beginning here as well. I know this is something that you're passionate about, and it's one of the topics that's one of our zones is covering here today. So I know you're passionate about it. What is Waygate doing to tackle this issue?
Waygate's doing a lot of things around this, and Baker Hughes, our parent company as well, so I'll talk a little bit about that. Diversity and inclusion is a huge part of our culture. It is part of a basic culture as you go through any links or so on Baker Hughes and Waygate. In addition, specifically, there is an interest in making sure that we are not only hiring diversity, and it's not, this is a very controversial topic because people say you cannot just hire because a person is of a specific gender.
Positive
we don't
discrimination,
do that.
Yeah.
We don't do that. So what we do is we make sure that every slate of candidates that come through, unless we have at least 50-50, we do not look at it. And the final winner will be based on the skills and so on in the interview, but we start to push people, the managers, to think about bringing in, and if people are not, if we don't have 50-50 on the candidate slate, then we continue to keep looking. So that's one. Second, we obviously have ERG programs as any other large company does. So we do employee resource groups and so on. And third, really, I think the company is I have a little daughter, 7-year-old, and my priority, she's my number one priority. And, as long as the work is done, they're always very flexible in terms of making sure they support and go through, the thought process, which I think it is really you are valued for your skill, not because of certain things.
So why do we need more women in STEM?
We need balance. Imagine you are tackling a problem. Take digital, for example. If everybody thinks in the same way, then you come to a conclusion and the probability to fail is larger. But imagine you had multiple points of view. And you vet your solutions so well because you get all the balanced views. So your probability of failure is much lower. And as we embark upon, the uncertain, volatile, complex, ambiguous world, it is very important to have that balanced view as leaders. And this is me not talking as a woman or as a mom, but talking as a leader. For me, it's important that we get that diversity of views. So when I go out there with new ideas, digital triplets, and so on and so forth, the probability of failing is much lower. So I think there is a balance, more of the balance, and currently the balance is tipped off, so we're trying to make sure, and this applies to many other things too, but specifically for women, I think that's a big topic.
Okay, great. We'll come back to digital triplets then, because that's the focus of the session. And there's a question here that's come in on the virtual audience. It says, what's your personal favorite use case when working on digital triplets? I
like additive because the whole manufacturing is in a box, and then you can actually see, dopamine when you can see immediately. When I showed the number of suppliers for an automotive and so on, there's more. So I think when you think about aerospace and automotives, the impact is probably much higher. But in additive, you get that dopamine kick because you can do the full circle and you keep seeing every part becoming better than the part before.
Okay, any final questions from the floor? Yes, one over here. Could we scoot the mic over there? Thank you, Tom Swallow. Doing a sterling job. If you just state your name and where you're from, please.
Yeah, hi, Cameron. I'm one of the presenters presenting soon, but I did have a question about diversity in workplace and obviously diversity of thought, and it's specifically more on women's being represented equally. Obviously, we've been trying a lot as well, trying to create that balance. The challenge is obviously the supply side. If you look at universities, the intake still isn't as much to be able to create that balance. There are things like apprenticeships where you can try and go around that. Have you had much success around that in leveraging those programs, something you could share with others to maybe learn as well?
Extremely good question. I think pipeline is a very important aspect of this. So we do a couple of things, right? So we start early with the STEM. We go to schools and so on and explain what engineering is, the world of technology. When I was a 7-year-old. I knew because my dad was an engineer, but really otherwise there was not much of an option to know. But we're doing that. Secondly, there are internship programs that are available. And in that case, we always do 50-50, try to bring 50% of women in it and 50% of, regular candidates. And so that kind of at least builds the pipeline. Eventually, do they actually take up the jobs or not is different. What we also do is for middle level women leaders. We have programs, leadership programs that helps focus on, women and men are different, and everybody is different, honestly, each individual is different. So we look at things that are, that they say that they need help with and development with, and we focus on those areas and give them development. So also not losing people at the middle management, right? So bringing them to the next level. Hope that answered your question.
Okay, thanks for your questions. That's all we've got time for. Thank you very much, Aru.
Thank you, Scott.
Thank you.